onto the processor. We've also expanded the number of cores, the amount of cache, and the amount of memory that every processor has on it. So now, where on a Gen 6 or 7 you had 36 lanes of PCI Express Gen 2 on a chipset that was a hop away from the processor, now you have 40 lanes of PCI Express Gen 3 on both processor sockets. So you have 80 lanes of PCI Express Gen 3 in a platform. So integrating PCI Express on the die gives us about 30% less latency because you don't have the hop. And then we've also doubled the bandwidth per lane, going from PCI Express Gen 2 to PCI Express Gen 3. And then we've also pretty much doubled the number of lanes available to a platform in a box. So you can think of it as quadrupling pretty much the amount of system I/O bandwidth in a server, which is pretty incredible generation to generation change. And I'll talk more about what the architecture of the platform looks like in a second. But due to this relentless march of integration that Intel has been driving, we've been seeing some pretty stellar performance gains generation to generation. So in this generation, you'll see 80% or better performance gain in floating point applications, for instance. Spec FP rate, we get a little better than 80%. In LinPack, it's more than twice as fast as the previous generation processors. Breakthrough I/O innovation, I hit on that. Trusted security. So on Westmere, which is the previous generation core, we had something we called AES-NI, AES new instructions in there. 7 new instructions that are useful for, we call it big number math. And if you hear anyone say big number math, that's code for encryption and things like that. So we also have something we call TXT, Trusted Execution Technology. And what TXT does is from the moment you power on a server, it hashes the BIOS, it hashes the hypervisors, and it stores those hashes in a TPM. And as the system comes up, it measures what it's booting, compares that against the known good hashes, and if there's a problem, if something doesn't match, it'll stop and scream. If you guys remember the blue pill exploit that was in the press about 2 years ago, the whole we'll root your BIOS and put some code in SMM and the OS will never see it, and you know, you guys are totally screwed if we figure this out. TXT will fix that, closes that hole. So that's kind of the point of TXT. And best data center performance per watt. What that means is we've got better than a 50% improvement in spec power virtual benchmark. So what it really means is we have a lot more advanced power management in the platform. We also have a lot more performance. So the way spec power works is for the amount of power put in, the amount of performance you get out, it's a ratio. So we kept the processor TDP, so the thermal design powers, the same. We had 130 watts, these are 130 watts. But the performance basically doubled, right? So we got a 50% bump in spec power. Any questions about anything I've said so far? I don't see anyone sleeping yet. That's a good sign. All right, so let's talk about E5 2600. And if you guys, if I slip and I call it Jaketown, that's because that was the, oops, back. That was the code name for this thing. At Intel, we have a couple of things that are Sandy Bridge. There's client Sandy Bridges and there's server Sandy Bridges. So if someone at Intel, talking to an Intel person, says Sandy Bridge, generally they mean the client thing. And if someone says Jaketown, they mean Sandy Bridge on server. And the reason that is, right, so we have cores and then an uncore, all the stuff that wraps around it. And a core is basically the core and its 2.5 meg cache slice. Everything else in the die we call an uncore. So that includes the power control unit, integrated I/O, QPI, the home agent, which is like the router on the chip, things of that nature. All right, so let's talk a little bit about the difference from Gen 7 to Gen 8. So you guys can really see how Intel and HP are able to deliver on a continual basis these large generation-to-generation performance increases. So if you look at the picture here, you see 4 DDR3 channels on each processor. In the previous gen, we only had 3. So it's a pretty large jump just in memory capacity in a box. In a DL380, DL360, ML350, servers of that nature, we've gone from 18 DIMM slots in a server to 24. So you can get up to 768 gigs of memory in a Gen 8 server, in a 2U or a 1U even, which is a ton of memory. We've also increased memory speed, so you can get DDR3 1600 in 1 DIMM per channel configs, and I actually think HP may have validated 2 DIMMs a channel. Not positive, I'd have to look. We've also added 2 more cores, so we went from 6 cores to 8 cores. On the previous gen, we had these QPI links routed in a triangle. We had a link between the processors, so a processor could get to remote memory and remote cache for snoops. And we also had a QPI link going to the chipset, so that each processor could get to I/O. Now, because we integrated the I/O, we don't need the hops down to a chipset anymore. So we have 2 QPI links running at 8 gigatransfers a second between the processors. So it's a gargantuan amount of bandwidth. We never get starved for bandwidth for remote memory or snoops or even remote I/O. It's a really good thing. And then 40 lanes of PCI Express Gen 3 per socket. So 80 total lanes of PCI Express Gen 3 in a platform. So just more stuff in the sockets. All right. Gary talked about the Smart Socket Guide. So this is actually what it looks like. I'll pass these around. This is the standard Intel Xeon 2600 E5 2600 processor, J-Town. You know, underneath this heat spreader here, there's a die. It's about that big. What HP did is they said, man, bent pins suck. People in their factories and the channel, right? HP sells both direct on the website, and they also sell through channel partners, value-added resellers. So people like CompuCom, Computex, CDW, TSA here in Houston, partners like that sell HP servers, and they can configure them, and they have to support them. Well, in the model, in a standard Intel model, you actually have to take your fingers and grab the processor and set it down on a pin field of 2,000 very densely packed pins. And what ends up happening is people, being the people that they are, a little clumsy, they'll hit the pins and bend them. And if you bend a pin, you have to trash the motherboard and replace it, and it's a big, big pain. So the way HP fixed this is they designed the Smart Socket Guide. So the socket's soldered down to the motherboard. There's a cage around it that is used to compress this CPU down onto the pins. The lid, we call that cage an ILM, an integrated loading mechanism. So the lid of this ILM, generally the Intel one will just sit down on the processor and push it down. Well, HP put little ledges on the side, and they take this Smart Socket Guide, and it springs in the hinge, it sits up like this, and with one hand you can drop this down on the lid. These 2 little holes here register it in the exact right spot every time, and when you push the lid down, there's a little slot in the hinge and a spring, and it'll push it up so the CPU levels out, and when you engage the camber arms to lock it in, it'll compress down. And what that does is it keeps people's fingers away from the socket. So they've pretty much eliminated user error for bent pins. So No more trashing motherboards, trying to fix them or upgrade them or things of that nature.
We're going to see those this afternoon. We're going to see that this afternoon when we go to the design center. They're going to show you this one.
Yeah. Yeah. So that's one of the quality innovations that HP's made on Gen 8. All right. Let's see what I got next. All right. So this is a diagram of what I/O looked like on the previous platform. So this is a single processor previous generation thing. So integrated it. Yep. Double the bandwidth. I hate build slides. Y'all like build slides? I hate them. That's right. There's another technology in E5 2600 that is called DDIO, Direct Data I/O, Data Direct I/O. And what this is without changes in drivers, the processor is smart enough to know what thread on the CPU is doing what, where, who requested that I/O, and if it's going to be used. So instead of going out to the network, requesting a packet, getting it back, and then sticking it in memory, and then making the CPU thread go back out to memory and grab it, brings it into cache, and then can do work, the processor is smart enough to go, oh, someone asked for that I/O, I'm just going to stick it in cache. So it removes the whole write it out to memory, read it back phase of that operation. So it decreases latency to data, basically. There you go. Let's see what's next. You guys ever heard of AVX? Advanced Vector Extension? Yes. So AVX is really slick. What we've done is we've taken floating point accelerated instructions. Sorry. On this mic. All right. So we've taken, we had AVX, SSE1, 2, 3. Now we have AVX. And what AVX does is it takes a bunch of the registers, expands them out to 256 bits, and it doubles the floating point throughput of a E5 2600 CPU. So if you look at a LinPack benchmark running AVX, you get greater than 2x throughput using this generation of processor versus the previous generation Xeon 5600s. One example of this, where Intel and HP partnered very closely, was before the public launch of this platform, Intel actually enabled quite a few supercomputer customers for the Top 500 run that was last November. And Intel and HP partnered at Purdue University on a cluster called Carter. And these guys are getting twice the performance with half the nodes, basically, of their previous generation supercomputer. It's a pretty large performance per watt gain for Purdue University, and they're doing all kinds of cool things on it. Cancer research and weather and who knows what else. Any questions about AVX? No. These instructions, because you get so much done in a short amount of time, they're actually very performance per watt efficient. As we go forward, you'll see there's a notion in power management called the race to halt. You try to get as much done as fast as you can and then turn everything off to save power. So you'll see some of these things in Intel architecture and HP Gen 8 as we go forward, more and more advanced power management. One of the other nifty new things we do in this platform is the second generation of Intel's Turbo Boost technology. If you look at a Xeon 5600 processor, when all the cores were active, you would get 200-300 megahertz of turbo at any one time. On this generation of processor, you'll get 4 or 5 or 6 bins of turbo, and if you only have one core active, you can get up to 9 bins of turbo. So on the top bin 2.9 part with all cores active, we'll turbo up to 3.3 gigahertz, or yeah, 3.3, and stay there depending on how much power the application's burning. This is really nice, and the technical reason we did this is different applications use different amounts of power. So on the Xeon 5600, we capped power at a TDP limit, 130 watts. On this, we'll actually go above 130 for 6, 7, 8 milliseconds at a time and come back down. So we're heating up the heat sink, and then we're using the thermal headroom that's already built into the platforms. So we'll heat up the heat sink. As it gets warm, we'll taper back off. What's nice about this, though, is there are a lot of usage models that just don't push the processor very hard. Integer-based computing actually doesn't push the processor that hard. We use the most amount of power when we're doing floating point apps, like LinPack or things of that nature. So if you're running a database server, or you're running, web services or things, the majority of real-world data center usage models that are highly integer-based, you'll stay in turbo a long time because the processor just doesn't burn that much power. So we just keep giving you the frequency, and we'll let you use more and more power up to, a certain point. So you get more bins of turbo for longer on this processor, especially if you're not using AVX and floating point consistently. Security. I talked about TXT and AES-NI earlier. That's it. Those are all the slides I have. I'll go back to the architecture one. So that's something to point at if we have questions. Build slide. Go away. Okay. So that's all the material that I brought. And I managed to do it all in 20 minutes. Let's talk about some of the other joint Intel HP innovations in ProLiant in general. Have you guys ever heard of dynamic power capping? You have. Good. So there actually is a special mode for HP only in Intel processors that enables them to do HP's flavor of dynamic power capping. And this was a partnership between HP and Intel. It goes back a long way in terms of engagement, because you guys might not realize this, but the length of time from when you start planning a microarchitecture to when you develop it to when you deliver, it's about 4 years, maybe even a little longer. Because when you build as many processors as Intel, we do a lot of technological pathfinding. So about 4 years out before we're going to get to a processor, the technologies have to be solid. And then as soon as the technologies are solid, then we decide what we're going to do, and we lock that down, and then you get into design, and then it takes you 12 to 14 months to, once you get silicon back, to actually ship it. So it's a long window. We've actually been shipping dynamic power capping since Gen 5. This version, it works in a similar manner. And what HP has designed it to do is to reclaim unused power from a data center. So you can cap a server to whichever power level you'd like to within a certain range. And if you have racks that you just can't power, you can't get enough watts into the rack, you can cap the servers and fill them back up. And that gives HP other capabilities, like the ability to move power around between application servers depending on a time of day or an SLA, right? You have some SLA for throughput of an application and it's not getting there. You can adjust the caps around, give this server more power, take it away from ones that aren't being used, right? Or you do backups at night. You can turn front-end web down and give backup servers more power, things of that nature. What's another one? Any random questions? I can keep droning on. Go, shoot.
Okay.
Choose your favorite.
Oh, you're gonna love it. Fair warning, I do device driver development. So.
I'm sorry.
Okay, yeah. Worst part, Ethernet. So, okay, so you mentioned that the E5s are very aggressive on the I/O caching. Now, is that exclusive to the i350 Intel Ethernet, or it'll do it with everything?
It'll do it with anything without driver changes.
Ooh.
That's what the CPU architects tell me.
Ooh.
Yeah.
We're gonna sign up to get a whole bunch of these for free and replace everything I own with them?
Yeah. It's pretty slick. And you guys, I don't know if you've ever heard of, Intel had a technology we called DCA, direct cache access.
Yeah.
This is improved DCA.
Ooh.
And our CPU architects, especially our network, a specific architect and networking guy has been working on this about 5 years. And he thinks he finally has it right.
Nice.
You know, if we don't have any other questions, we can wrap early. We don't
Yeah.
have to have you drag up there. If you're good, think of anything else?
Well,
Let us know. If not, we can take a break for a little while, go from all things here.
So I'll talk a little bit about just the amount of, yeah, we'll spend 5 minutes chatting about this and then end. Talk a little bit about the amount of time and give you a feeling for how long we've been working on Gen 8s. We started doing initial architecture work with HP on Gen 8 in early 2000, no, it was late 2007. It's been over 4 years we've been working on this, and this processor, the Xeon E5 2600, when Intel planners and architects were looking at the ecosystem, we went, okay, what's the best-selling server in the world? It's the HP DL380. So, all right, that's our design target. Let's build a processor that is badass in a DL380 and fits everywhere else too. So this guy was actually pretty much purpose-built for DL380s and HP architecture. HP 2Us, blades, racks, everything like that. And it fits very well in HP's ecosystem, in their servers. So yeah, so we started architecture work about 4 years ago. We got first silicon back about 1.5 years ago, and we've been debugging, improving, adding features ever since then. And we finally got it launched this March. Too much joy and happiness in the engineering community. And that's it. I'm kind of out of shtick here.
Okay. Well,
Unless there's any questions. No?
No questions.
I actually remember some of you guys. You remember doing this on Gen 6? I remember you, Scott. I think I posted on your blog once. It was a turbo thing on the Halem.
Mine or the other Scott Lowe?
Oh, is there another Scott Lowe?
He's
Yeah,
the other
he's
Scott
the
Lowe.
other Scott
Oh, man, I'm sorry.
It happens a lot.
That's okay, there's that third Scott Lowe.
Yeah, the one that's with the birch.
Yeah.
Yeah.
All right.
I got a congratulatory message for his new job.
That's funny.
That's funny. Well, thank you
All
very
right,
much,
guys.
Chief.
I'm done.
Thank you.
Guys, I guess we'll kind of stretch our legs again. We've got some time. Trying to see if we can get John Jamala and his folks down here a little earlier, but if not, we'll just take it easy for a few minutes. You've got about a half hour before we think that we get going.
You was the driving force.
I know.
Let's say, because you want the driving force.